Yeah. Hello, Munu.
यस सर।
Yeah, regarding the assignment, तुम मुझे एक बार वो स्क्रीन प्रेजेंट कर सकते हो? Can you please present the screen?
यस सर, अभी कर।
Let me see. Actually, तुम्हारा पिक्चर देख के मुझे समझ में नहीं आया. I couldn't get that. What was the question?
सर आपको मेरा स्क्रीन शो हो रहा है?
Yes, yes. Showing screen.
सर क्वेश्चन दिखाओ या फिर वो सॉल्यूशन?
Question solution दोनों दिखाओ. दोनों. I need to
यस
see.
सर, अभी।
Okay.
सर यही था। सर आपको दिखाई दे रहा है क्या मेरा स्क्रीन?
दिखा दे.
यस सर, ये दिया था।
Okay.
साइनोग्नाथस।
Research.
सर इस फसिल को डाटाबेस, पालियो डाटाबेस साइट पे जाकर उसका, सर उसको चेक करना था उसके बारे में। सर हमारा पहला तो ठीक हो गया, साउथ अफ्रीका और अफ्रीका।
हाँ.
लेकिन सर ये उसमें शो करा था टेरेस्ट्रियल, लेकिन यहाँ पर आंसर दिया है बोथ।
अच्छा. साइनो मतलब साइनोगोथस का जो इकोलॉजी होगा. ओके. वो क्या
यस
होगा?
सर।
रुको एक बार मैं ये चेक करता हूँ. 1 सेकंड. गिव मी अ सेकंड.
Yes,
ओके. देखो साइनोगोथस जो है ना वो मेनली लैंड पे ही रहता था. ठीक है.
सर। सर हमने लैंड उस पे भी, सर वो पायलट डेटाबेस के साइट पे भी यही दिखाई दिया कि लैंड, लेकिन यहाँ पर
बट
लैंड
बट
में।
बट कुछ कुछ आर्टिकल में ये दिखा रहा है कि देयर आर सम साइनोगोथस लाइक क्रिएचर हु वुड हैव मतलब दोज हैव वेंचर्ड इन वाटर बॉडीज बट दे डिडंट लिव इन वाटर बट दे वेंचर्ड इन वाटर बॉडीज but they were majorly used to live in land only. Why did it live? So it will obviously live in land. The correct answer will be land.
Yes, sir.
Okay. And
सर another question है सर वो नंबर फोर्थ सर वो ट्रायसिक में दिखाई दे रहा है ओनली ट्रायसिक में दिखाई दे रहा था इसके अलावा और कोई भी पीरियड में दिखाई नहीं दिया लेकिन यहाँ पर मैम ने दिया है परमियन
specific color only Permian. तुमने क्या क्यों दिया था?
सॉरी सर
ट्रायसिक दिया था. 1 second. Two 47.2 to 228 million years ago.
सर जो डाटाबेस पर वो पर्पल मार्क्स ही पा रहा था
1 second. हाँ वो तुम्हारा ट्रायसिक ही तो होगा. परमियन तो नहीं होगा क्योंकि परमियन इज योर 252 मिलियन ईयर्स अगो, राइट?
यस सर
परमियन नहीं होगा. 247, 228 से 247, तो दैट इज नॉट
वो तो
परमियन.
ट्राइस
ट्रायसिक. ट्रायसिक वुड बी द आंसर. देखो अब ये और एक जगह और ब्रिटानिका में ये तुम्हारा शो कर रहा है. अ, अरे यार ये तो अभी ब्रिटानिका में 251 शो कर रहा है. बट उसका टाइम पीरियड तुम्हारा ट्रायसिक होगा, ठीक है?
यस सर
इट विल बी ट्रायसिक, एनेशियन ऑफ द ट्रायसिक. वो ट्रायसिक हो, परमियन नहीं हो. क्योंकि
तो फिर ये जो
हाँ बोलो.
क्या बोल रहा हूँ सर ये जो ये टू क्रेडिट पॉइंट हमारा
ये
माइनस हो
ये दो आंसर, एक काम करूंगा मैं, ये दोनों का आंसर तुम मुझे ये वीकली ये तुम स्क्रीनशॉट ले सकते हो.
यस सर
So if you can take a screenshot, you send the screenshot to me in the mail. So I will talk to the this course coordinator. Okay.
यस सर
Okay.
थैंक यू सर
Okay. Okay. So
सर वो जो असाइनमेंट वन का भी था उसका भी भेज दूं क्या आपको जो माइका वाला
माइका वाला, दैट इज नॉट नेसेसरी माइका वाला, क्योंकि हाँ भेज दो भेज दो भेज दो.
थैंक यू सर
Okay. So excellent. Okay. So I will start today's class with isotope geochemistry. Okay. Now, yes. Okay, okay. It's PPP. My screen is visible, right?
Yes, sir.
Okay. So now, first of
Sir,
all, I will start with the basics of the isotope geochemistry. And today in this
सर
class,
मैंने आपको सर
uh,
सर मैंने आपको मेल कर दिया.
okay, okay, it's not a problem. Okay, okay. So for today's class, I will start with the rubidium strontium isotopic systematics and here binary mixing, the concept of binary mixing. So I will start with the basic lecture of radioactive decay, and I will be deriving the radioactive decay, uh, the equation of radioactive decay, so that you all guys can better understand the prospect of isotope geochemistry. Now, let me go through what are isotopes. Now, isotopes are different nuclear species, okay, of same chemical component. They have same atomic number but different nucleon number. Nucleon number means uh, it is equivalent as the mass number, okay, and it is the number that indicates the total number of protons and neutrons, okay. So mass number equals to number of protons plus number of neutrons. So this is all about isotopes. Now, isotopes are of two types. One is the stable isotope and another one is the unstable isotope. This unstable isotope is also known as your radiogenic isotopes. Okay. So these radiogenic isotopes actually fluctuate from the value of beta stability. Now, if this is the zone of beta stability, then all the stable isotopes lie in this zone. Whether that isotope would be a stable or unstable one, indicated by the or demarcated by the zone of beta stability. If the isotope falls here, then it would be a, if it deviates from this line, then it would be a unstable or radiogenic isotopes. Fine. Now, how actually we can say that whether the isotopes is a stable or whether the isotope is an unstable one. So it depends of a certain factor. So on based on that factor, we actually tells or there is a mechanism behind that, and that mechanism or that process is called a decay process. And when that process occurs in uh, these isotopes, or the process is mainly called known as radioactivity, and this decay is specifically known as a radioactive decay process. So this process actually tells us about the spontaneous transformation of one radioactive nuclide into a daughter nuclide. So for an example, if there is a radioactive nuclide X. So if it is unstable in nature, if it is radioactive, then if it is a radioactive nuclide, then in this universe or in the nature, everyone or every element tries to be in a stable state configuration. So ठीक है, तो मतलब जो भी एलिमेंट होगा तो इट विल ट्राई टू अटेन इट्स स्टेबल कॉन्फ़िगरेशन और स्टेबल स्टेट at least, because in the stable state the energy level is minimum. So when the energy level is minimum, that it actually satisfied all the criteria and it is stable basically. So in order to do that, in order to gain stability for an unstable or radioactive nuclide, it produces or it generally spontaneously transform into daughter nuclide, which may be a radioactive or may not be a radioactive one, with the emission of one or more particles or photons. So what it does is it basically release energies in the form of photons or particles to gain or attain a stable position. And this process, this entire mechanism or process is called radioactive decay. Okay. And always remember this process of radioactive decay, if for a certain element X, and if it uh, spontaneously transform into its daughter nuclide. So we will be covering in today's class the RBSR isotopic systematics. So let's take the example of rubidium. So rubidium has two natural isotopic systems. One is 85 rubidium and one is 87 rubidium. So 85, and among these 87 is the unstable or the radioactive or the unstable isotope. So let us consider the case of 87 rubidium, right? So if we are talking about 87 rubidium, it will be transforming into by a spontaneous process, it will transform into strontium, right? 87 strontium. Now when it transform into 87 strontium, it will go under certain mechanisms or certain reactions, right? Now these reactions, they will follow a path, and every radioactive decay path is followed by a first order kinetics. Fine. Now what is first order kinetics? First order kinetics means the reaction in which the rate of reaction is directly proportional to the concentration of the reaction. Okay, it means, or what I mean to say is, it will follow a straight line. It will follow a straight line. Okay, means it will follow y equals to mx plus c time with a negative slope. Now you guys may ask me a question that why it will follow a negative slope. Because every parent nuclei, when it will transform into its spontaneous daughter nuclide, if or may not be a radioactive one, irrespective of that, what it the process is going on, it is going through a process of decay, means it is losing something, right? Then with respect to time, so here the function is time. So by keeping the technical term time with respect to time, or by assuming that everything is a function of time, they are decaying the process in, they are losing something, right? So the graph will look like this. So with respect to time, it is delineating, it is decreasing. That is why it is a function of negative slope. The first order kinetics with an equation of straight line y equals to mx plus c with a minus k with a negative slope. Okay, so please do remember this. And another thing is that it cannot be influenced by some factors, some that is chemical or physical factors, such as temperature, pressure, and volume. Temperature, pressure, and volume. This cannot alter, or this cannot change the process. Okay, these physical or chemical factors, they have no role to play or to make changes in this radioactive decay process. Now we will start with the rubidium strontium isotopic geochemistry. Okay, now this rubidium strontium isotopic geochemistry, or the isotopic systematics, this RBSR isotopic systematics, is a very fundamental and important isotopic systematics which is used in geological sciences or various discipline of earth sciences. It is a robust proxy. It is basically used for provenance study. It is used to study what kind of rock or mineral is forming. It is used to find out age of particular rock or mineral. Okay, so these are the broad areas that is covered by the RBSR isotopic systematics, right? Now, so what is rubidium? And rubidium is basically an uh, alkali metal, right? Now, in case of rubidium, it has two mm, naturally occurring isotopes. One is 85 rubidium, atomic number is 37, and one is 87 rubidium with an atomic number 37, because these are same chemical elements, right, but with different nuclear species, so their mass number just have been changed with the by keeping the atomic number constant. Now, uh, before going into the details of RBSR systematics, I will just show the derivation of how we actually derive the decay constant and how we obtain the equation that n equals to n naught e to the power minus lambda t. So we know that the rate of decay is proportional to the parent nuclei. And if we consider the rate of decay as A, it is proportional to the parent nuclei N, right? Now, if any isotope is unstable or radiogenic, then it will undergo through the process of decay. And if N is the number of parent nuclei and A is proportional to N, so we can write A equals to dN by dt. It will decay with respect to time because it is a function of time, right? And if a equals to dn by dt, then we can write dn by dt is proportional to n. Now, if we lift the proportionality constant, then another proportionality constant term will be there, that is lambda, and lambda is the radioactive decay constant, right? Now, I will tell you the significance of the negative sign here. There is a very big significance of the negative sign. So this negative sign actually indicates the uh, that, or it tells that the n decreases with time t. So if we rearrange this, the equation will look like minus lambda dt. Now if we integrate on both sides, log of n equals to minus lambda t plus c. Now at t equals to 0, n will be n naught. Initial number of, what was the initial number of parent nuclei, right? At t equals to t0. Now log of n0 equals to,
हेलो
yes,
सर आप लोगों को लॉग ये लिखा है ना एलएन के रिप्लेसमेंट में
log n naught,
ये
yes,
सर आप लोगों को जो लिखा है ना लॉग ई बेस सर लॉग एन बेस ई सर वो लॉग ई आपने एलएन को रिप्लेस करके लिखा है ना
हाँ हाँ
जो
हाँ, हम्म,
डेरिवेटिव
so c equals to log of e n0. Now if we put the value of c in this equation, the log of n equals to minus lambda t plus log of n0 e. So log of n minus log of n0 base e equal to minus lambda t. Now it is the property of log, that log m by n equals to minus lambda t. Now n by n naught equal to e to the power minus lambda t, or n equals to n naught e to the power minus lambda t. A very simple basic equation. So we have derived it. Now we will know about, or study about rather, the isotopic systematics of rubidium and strontium, right? Now in order to study that, we have to first know about this systematics of rubidium and strontium. So we generally write the equation for 87 rubidium is, it will decay into 87 strontium, and strontium has an atomic number of 38, plus there will be a beta negatron plus an anti-neutrino, plus it will release an energy that is 275 kilo electron volt. This is anti-neutrino. This is the reaction or equation, we can say, when rubidium decays into strontium. Now, strontium has four naturally occurring isotopes. 84 strontium, the abundancity of 84 strontium is 0.56 percentage. Please do remember this. 86 strontium is 9.87 percentage, and 87 strontium is 7.04 percentage, and 88 strontium is 82.53 percentage. So the highest abundance is shown by 88 strontium. Okay, now, so we know that Rb is an alkali metal, and it falls in 1A in the periodic table, and it has an ionic radius which is in the order of 1.48 Armstrong, right? And I think you guys must be knowing that this number 1.48 Armstrong, and it is quite similar to that of potassium. Potassium has an ionic radius of 1.33 Armstrong. So, because of the comparable ionic radius and oxidation state, rubidium often replaces potassium in a lattice. Fine. So, if a mineral K is found as a major element, so it also means that somewhere, somehow, rubidium can fit into its structure, can fit into its lattice. So generally K is found as a major element, whereas rubidium is found as a trace element. Now, or sometimes we can do from the spectrographic studies, if we plot this abundancity, we will see that if we plot 84, 85, 86, 87, 88, we will see 84 there will be a peak 0.5, 86 there will be a peak of 10%, for 87 there will be a peak of 7%, and the rest peak, this is for strontium isotopic system, it is 83%. And similarly for 84 there will be a flat peak for rubidium. 85 there will be a peak for rubidium, again it will go flat, then it will, the highest peak of rubidium, again it will go flat. So this is the rubidium, this is strontium, this is strontium, strontium, strontium. So when we do the analysis actually for trace element analysis, so for an example, if we want to quantify a sample, that that particular sample, let's say the particular sample as any sample, any name you can give it to that sample. So for an example, we give a name called SS, that for that particular SS sample, if we want to study the provenance or the origin of the sample, so for that purpose, if we are doing a trace elemental study, say for an example, we want to characterize or just quantify the concentration of rubidium strontium isotopic systematics present in that sample, and by comparing with the RBSR values, we will just compare the RBSR of any standard values of any some known locations. So for an example, if we have collected the sample from river Narmada or for river Ganges, so if we want to determine that, so what, from what rock that rubidium or strontium have
सर
been.
हेलो
Yes.
सर आपका स्क्रीन विजिबल नहीं हो रहा
Screen is not visible.
नो सर
Okay, 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 one second, one second. ये कितने मिनट से विजिबल नहीं है अभी?
ये सर अभी अभी
Okay, okay, one second. I think there is, due to network connectivity issue. It's visible, right?
Yes, sir.
Okay. Now, when we do suppose provenance study, we are using a sample which we have collected from, let's say, river Narmada or any other river, let's say river Ganges. So when we are doing trace elemental study on that particular sample, via various processes. First, we have to go through the process of column chromatography. We have to dust the sample, powder it. Then we have to do acid digestion. Then it will be ready for your mass spectrometrical studies. Now, so everything is fine. Now, when we will analyze the sample, right? So, yes. So we will be studying it for rubidium and strontium concentration. So when you are analyzing the sample for rubidium or strontium isotopic studies, we will have to know that the rubidium or strontium value of any known place. So for an example, that if this much rubidium or this much strontium is present in the sample, if it is showing this much parts per million or parts per trillium of Rb or Sr, then this sample must have been originated or must have been supplied from the HHC, higher Himalayan crystallines. Okay, or if it is from Narmada, if the rubidium or strontium isotopic values are very low, and if that sample contains high SMND or epsilon ND values, then we can say that SMND means it is a basaltic source, or high RBSR means it's a granitic source. So the straight way one thing will come to your mind, oh, it's a granitic source, then it must have the, the higher Himalayan crystallines, the granites of HHC must have been the contributor of this RB and SR which is present in the sample which have been collected from Ganges. If the SMNT value is high, then oh, let's straight away think, you will straight away think of what, the basaltic source rock, right? So from central India or western part of the India. Now, so this way we can use these RB and SR isotopic systematics to for the provenance study, and it is also a very good proxy for paleoclimatic studies also. Now, so coming back to the RB-SR systematics, so it is very likely that potassium-rich mineral is likely to host rubidium, mainly because of its similar ionic radii and oxidation state, because one can replace the other easily. And
सर
same,
तो फिर
yeah.
सर तो फिर माइका से सर रुबिडियम आने का कोई चांस है?
Yes, if your mica is containing potassium, then that potassium can be replaced by rubidium.
यस सर, यस
If that,
सर। इसी वजह से क्या वो जो जो ग्रेनाइट में थोड़ा माइनर अमाउंट का एक्सेसरी मिनरल की तरफ माइका बिहेव करता है, तो फिर इसके वजह से रुबिडियम मिलता है हमें ग्रेनाइट से?
इसकी वजह से,
रुबिडियम मिलता है क्या ग्रेनाइट से?
yes, yes, that's why we find rubidium granites actually. क्योंकि देखो,
यस सर।
this rubidium, and one more thing is that the rubidium and strontium, these are a group of particular group of elements, right? So these are they fall into the category of incompatible elements. So incompatible element means when, suppose, the rock is at a very greater depth, right? So at that depth, the rock is undergoing a very high heating path. So if you heat the rock with a very high temperature, it will tend to go under melting process, or it will be partially melted. Now, if that rock is partially melted, what it means to be a partially melting, what it means to be undergoing the process of anatexis is that the rock have not melted completely. It have been melted partially. It means it has a melting part and it is a residue part, residue hard rock part. So the tendency of the incompatible elements is to be in the uh, fraction of the liquid, so it will not in the residue, it will tends to go into the liquid part, right? So, and that residue or and that liquid part, after some time it will crystallize, right?
Yes, sir.
It will form a separate layer. Then again, suppose that layer is b, again that b layer, if you are providing with high temperature, again it will go into the process of partial melting. And further, when there will be partial melting, again there will be some incompatible elements, again there will be a residue, so they will not live with the residue, they will actually move out from the residue, again they will go with the melt. And when they will be going into the melt, that melt will finally crystallize, and that melt actually forms your granitic rock, right? And that is why the incompatible elements are tend to be more found in the granitic rocks. So Rb is a incompatible element. As compared to strontium, Rb is more incompatible, right? But that doesn't matter, because Rb is a we know that there is an isotope of rubidium, that is 87 rubidium, which is radioactive in nature. And if it is radioactive, it means it will be unstable, it will not be stable in that form, it will convert it into the strontium. And if it converts or transform uh, with a systematic process into strontium, then the amount of radioactive rubidium which is present in your system, with function of time, it will be converted into strontium, right? So now, if your rock contains higher amount of rubidium, radioactive rubidium, then after a certain period of time, let's say x period of time have passed, you will be only left with strontium. Get it? So now, do you understand the concept? So your rock will be left with complete strontium. But there might be some rubidium, because 85 rubidium will be also there present. So that's how the system works. Now, uh, so for the strontium, so calcium actually is a good proxy for strontium, because calcium generally hosts strontium. Because as I have told you that potassium, the ionic radius of potassium and rubidium are similar, and their oxidation state is also similar, so one can be replaced for the other. So similar way, in that same way, Ca rich minerals, these are likely to have strontium, such as apatite, Ca rich, plagioclase, etc., etc. Now, let's say in a mineral the potassium by calcium ratio is high, then it is obvious that we will get a high rubidium by strontium ratio. And if we have 87 rubidium, then over the period of time we will likely to get 87 strontium, because it will decay it into the other. Now, so I will rewrite the equation which I have started with. 87 rubidium, 37 is the atomic number, 87 strontium, atomic number is 38, plus a beta negatron with an entry neutrino, plus 275 kilo electron volt energy. Now, we know that T half is 48.8 into 10 to the power 9 years. Now, we will derive the equation. So, 87 strontium equals to 87 strontium initial, this is 87 strontium at any time t, okay, plus 87 strontium which have been obtained by the decaying of rubidium. This will be your total amount of strontium total at any point t. You will have
Yes,
the
sir.
87 strontium initial with what have been decayed from the rubidium source. Now, we can rewrite this as strontium at t equals to 0 plus 87 rubidium at t equals to 0 minus 87 strontium. So it's like if you have 100 atoms and you have 30 atoms, so the difference will make 70 atoms. So means previously you have 100 atoms, 30 have been decayed, you are left with 70 atoms. So that is the case. So it means that much amount of Rb has decayed from your system and produced strontium. Now, so, and please do remember, for the rubidium case, as it is decaying, it is difficult to go back in time. So instead of writing t equals to 0, we will, or we can rewrite it in today's terms, means at the present day. Okay. So means if n equals to n0 e to the power minus lambda t, then n0 equals to n e to the power lambda t. We have to multiply this e to the power lambda t with the equation 87 Rb
Yes, sir.
at present time t e to the power lambda t minus 87 Rb of t. Now 87 SR of t equals to,
हेलो सर, थोड़ा प्रीवियस लाइन पे जाएंगे। सर वो जो ई टू द पावर लैम्डा टी मल्टीप्लाई किया ये समझ आया, लेकिन सर 87 रुपये माइनस किया सर।
अच्छा ये दिस
नहीं
पार्ट।
सर, प्रीवियस लाइन नहीं सर, आपने अभी जो लिखा ना स्ट्रोंशियम 87 when t equal to 0 plus रुबिडियम 87 t when t is equal to t मल्टीप्लाई बाय e to the power lambda t, लेकिन सर अभी जो माइनस किया ना सर वही थोड़ा जो।
Okay, so see, this part of strontium has what have been obtained by the rubidium, right?
यस सर। नहीं सर वो समझ आया, लेकिन सर अभी आप जो लाइन लिखे, अभी जो लाइन लिखे आप सर थोड़ा नीचे जाएंगे क्या? ये सर वो जो फर्स्ट लास्ट लाइन लिखा है ना अभी आपने, एस आर 87 टी इक्वल टू 0 प्लस आर बी 87 टी मल्टीप्लाई बाय ई टू द पावर लैम्डा टी। सर अभी जो ये जो माइनस टर्म लिखा है सर ये समझ नहीं आया, माइनस रुबिडियम 87 टी। सर इसको थोड़ा बताएं।
अरे ये तुम्हारा e to the power lambda t minus 1 हम लोग जो लिखते हैं ना, e to the power, we
ये
what,
सर।
see, what we write is, if there is an 87 strontium, and if there is an 87 strontium t equals to 0 plus 87 strontium of rubidium, so if we are getting the rubidium source, right, मतलब देखो, ये सोर्स हम लोग को कहाँ से मिलता है, वी गेट दिस सोर्स फ्रॉम दिस स्ट्रॉन्शियम सोर्स फ्रॉम 87 of Rb, right?
यस सर।
And uh, this, sorry, one second, I have done this mistake. ये तुम्हारा जो होगा, ये 87 of Rb of t होगा. Okay,
यस सर।
now it is clear.
यस सर, यस सर, यस सर, अभी क्लियर है। यस सर। सर
So
वही जो कंज्यूम लिए थे सर इसलिए थोड़ा कंफ्यूज। यस
हम
सर।
लोग जो
हाँ।
100 से 70 डिफरेंस करते हैं, वो हम लोग तुम्हारा जो, मतलब we take the difference if there is 100 atoms and at the present day if there is 30 atoms, so 100 minus 30 we will get the elapsed, so how much it has decayed. So that is what we needed, right?
यस सर।
So no, sorry for the strontium. And yes, so whereas yeah, t equals to 0 plus, yeah, we can write 87 rubidium of time e to the power lambda t minus 1. Now we have arrived at a concluding point. Now we know that 86 strontium is the stable isotope and that is not going to change significantly over a period of time. मतलब ये जो तुम्हारा isotopes है, ये सब तुम्हारा over the period of time it may change because these are not stable isotopes, these are radioactive isotopes. So in order to maintain the consistency of the equation, what we do is we divide this each term with a stable isotope term, means a known value which will remain constant, which will not change, so that we can compare with the known value, okay, for our mass spectrometric studies. That is why what we do with the equation, we just play a little game with it, with this equation, that is we divide with a stable isotope, that is 86 strontium. So our equation become 87 strontium by 86 strontium of T equals to 87 strontium by 86 strontium at T equals to 0 plus 87 rubidium by 86 strontium of T. I am writing e to the power lambda T minus 1. So this is the main equation. Is it okay?
Yes, sir.
Okay. Now, is my sound is echoing?
Yes, sir.
Okay. 1 second. What to do? Now is it fine?
नहीं सर अभी थोड़ा थोड़ा हो रहा है.
Okay, 1 second. Is it fine now?
Yes, sir.
Okay. Now, so yes, so we have arrived at this equation. Now if you look carefully at this equation resembles like a equation of the straight line, y equals to mx plus c type, right? So this is your y, and 87 strontium by 86 strontium, we can rewrite this as, this is a constant term, and e to the power lambda t minus 1, this is your m, right?
Yes, sir.
And this part is your x. So it
Yes.
actually represents the y equal to mx plus c type. Now there are some unknown in this equation. There will be, when the question will come and you have to use this equation, this term there will be an unknown. Okay, there will be an unknown, and this time t will be an unknown. So we can actually uh, make out this unknown path. How? We can follow a graphical approach. So I will show you. If we draw a graph and if we put 87 RB by 86 SR and 87 SR by 86 SR in this part, and if we assume that the ratio of 87 strontium to 86 strontium is constant, that is T equals to 0, then if we take a rock and if we cut it into let's say 3 pieces, 1, 2 and 3, so we will take these 3 pieces and we will do analysis on these 3 pieces. Let's place this on this line, because for that rock the strontium ratios, that 87 strontium by 86 strontium ratios is constant, because within a same strontium isotopic systematics, the there cannot be a heterogeneity within the strontium itself, but in the but in the x part, that is 87 rubidium by 86 strontium, there might be a heterogeneity, because rubidium and strontium have different chemical systematics. So due to the different chemical composition or due to different chemical system, the amount of rubidium and the amount of strontium may vary within the rock, right? Now here we will be having samples having heterogeneities in the RB by SR ratios, because RB and SR have different chemistry. But on the other hand, we are keeping the 87 SR by 86 SR as a same chemistry, means having homogeneity in case of strontium ratios, that is 87 by 86. But these three sample will decay and there will be a loss of 87 rubidium and gain in 87 SR. So if this is x axis is your rubidium, and with time it is decaying, right? But your rubidium will decrease with respect to time, and rubidium will be converted into, or it will increase or tend to increase towards strontium, because rubidium is transforming into strontium. So you will get a negative slope, right? And this line is called the isochron line at t equals to t, time equals to t, and this is t equals to 0. Now the y-intercept gives us the initial 87 SR by 86 ratio. So this is our y-intercept. So this value, it indicates one thing, the 87 SR by 86 SR initial value, right? So from this we have already obtained the initial 87 by 86 SR, right? So when the rocks actually gets crystallized, we will come to know about the age when the rock have crystallized, right? And we know that the slope m equals to e to the power lambda t minus 1. So e to the power lambda t equals to m plus 1, and lambda t equals to ln of m plus 1, t equals to 1 by lambda ln of m plus 1. So from this equation we can calculate the time, right?
Yes, sir.
Okay. So we have came towards the conclusion that if we are looking for the sample of some age, then we will follow, or it will follow, a single straight line path, and that path is this. So it has been proved. Now this RBSR systematics, or this equation specifically, particularly to say, it depends on certain assumptions. Now the assumptions are the systems has remained a closed system since its crystallization, means no exchange has taken place within the system. It has to be a closed system. There is no gain or loss of RB by SR, right? Second, it depends on the homogeneity of the initial strontium isotopic ratios, because within the rock there couldn't be a heterogeneity within the strontium chemistry. If there are from the start, if it is not constant, then we will not get your y-intercept, right? Then you will not get a straight line, because it is a very critical assumption. And third and most important is, we need to have a heterogeneity in the RB by SR ratios. And in nature, or in natural systems, we actually get heterogeneity, because for an example, if you are considering a rock and if it has formed through natural processes, then you cannot expect to be of having same amount of rubidium and same amount of strontium composition in a rock, right? You will get varied composition of rubidium and strontium within that particular rock. Am I right or wrong?
Yes, sir.
Yes. So we need to have heterogeneity in rubidium by strontium ratio. And if that is not happening, then it means, just if it is having same rubidium by strontium ratio throughout the rock, what it means, we are sampling the rock. So for an example, we have taken 4 points and all the 4 points have same RB by SR. So what it means, so what will make the sense of doing a sampling of that rock, because it will have a one common point, and from that one common point the data spread will be less, right? So the accuracy will be very less. So it means it will not be a precise data, right? So we have to cover maximum number of data points, maximum region we have to cover, right? So, and particularly this heterogeneity depends on the potassium by calcium ratio, because the more the heterogeneity of potassium by calcium ratio, so more it can accommodate varied composition of rubidium and strontium, right? And we will have better data spread. But often these systems gets disturbed, that is, they are likely to subjected to metamorphism, right? So metamorphism can hamper these natural systems, it can restart the natural systems, right? So if a rock has crystallized at some age or at a certain age, right? Let's say 3.8 billion years ago, that is the age of a particular rock. Means the crystallized or the formation time of that rock is 3.8 billion years ago. But when we are dating some of the minerals from that rock, for an example, we are dating the apatite from that rock, or we are dating the biotite mineral, and the correspondence age of that rock is say 2.2 billion years from dating of that particular mineral, right? What it means is that rock have been restarted, or the rock have been subjected to metamorphism at that particular time frame, in and around 2.2 billion years ago. Means that is not the actual age of the rock, that is the metamorphic age of the rock at the time period, or at the time when the rock has been undergone the process of metamorphism, when it has gone through the process of metamorphism, right? But we have to
Yes, sir.
also keep in mind that in case of metamorphism, there has to be a mineral scale change. Means if there is a mineral scale change, I will show you the diagram. Let me explain it to you first. If it is a mineral scale change, means a rock is composed of several minerals. Let's say X, Y, Z, M. X, let's say X is apatite, biotite, plagioclase, olivine, blah blah blah. So it is constituent of different framework of different minerals. It is an aggregate of minerals. That is what we call the rock, right? And if
Yes, sir.
there are several minerals in that rock, so the metamorphism, let's take an example of dynamic metamorphism. It means, what do you mean by dynamic? It is going through a pressure temperature change. The rock is not changing, the composition of the rock is not changing, right? The metamorphism is in such an extent, only the minerals are redistributing, or the minerals are reorganizing itself. what it means is, एक मिनरल के साथ एक मिनरल का रिएक्शन हुआ, ठीक है? तुम्हारा जो कैल्शियम और पोटेशियम परसेंटेज इज देयर इन द रॉक, और द रुबिडियम और स्ट्रोंशियम परसेंटेज इज प्रेजेंट विद इन द रॉक, द concentration is not changing. Means the concentration is redistributing. Means पहले जो एपाटाइट था उसमें रुबिडियम का परसेंटेज 0.6% था, और in the plagioclase it is 0.4%. After metamorphism, the plagioclase has rubidium of 0.5 percentage, and that apatite have 0.4 percentage. If you sum them up, it will be, the value will be a fixed value, whatever it is, the total value will be fixed. Do you get it?
Yes, sir.
The
सर
composition.
सिर्फ अमाउंट सेम कांस्टेंट रहा है, लेकिन उसका थोड़ा वैरी कर रहा है कंपोजिशन। ये इतना रेशियो था, बाद में क्रिस्टलाइजेशन के बाद ये थोड़ा चेंज होकर कुछ अलग मिनरल का रेशियो थोड़ा बढ़ जाएगा, यही ना?
Exactly. Means it will try to reorganize itself. Means थोड़ा सा पार्ट यहाँ से यहाँ चला जाएगा, वहां से यहाँ आ जाएगा, okay? So it will redistribute or reorganize among itself, nothing else. That that should be your mineralogical changes in a mineral scale change. And what is a rock scale change? Means the entire rock will alter. Means the rock has melted in such a way, it has been melted completely. Metamorphism was so intense that it have completely melted the rock, and somewhere the rock composition has altered. And if you date that rock, then you cannot do the you cannot find its age. So the metamorphism has to be in such an extent that it has to be a mineral scale change, not very intense. So if it is very intense metamorphism, then you have to bury the rock at a very greater depth, then you don't know where exactly the rock was, then you cannot even trace that rock. Okay, so that was my point. Now, and also for okay, so we will see. Okay, we know that e to the power lambda t, right? Now if we do a Taylor expansion to find the precise edge from a metamorphic restarting edge, we need to do first this term, we have to undergo through a numerical expression of Taylor expansion. So what Taylor expansion tells us, it will be 1 plus lambda t plus lambda t square 2 factorial plus lambda t 3 3 factorial plus dot 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 dot. It will go up to the nth term, right? But in case of metamorphism, if there is a mineral scale change, the higher order terms will be neglected. And for low lambda values, means if the we ये भी एक assumption है that the lambda value should be minimum. Okay, for low lambda values we can obliterate this higher order terms. So e to the power lambda t will be left with 1 plus lambda t. Okay, so we know that e to the power lambda t minus 1 equals to, क्या लिख सकते हैं, 1 plus lambda t minus 1, 1 1 cancel. So in place of e to the power lambda t minus 1, we can write lambda t only, and we will just reorganize our equation. So 87 strontium by 86 strontium of t equals to 87 strontium by 86 strontium of t equals to 0 plus 87 rubidium by 86 strontium lambda t. So this will be our equation if the rock has undergone metamorphism, right? So हम लोग in replace of that we will use that equation if to find out the metamorphic. Now if we find plotted graphically, what will happen? So at this point RB by SR equals to 0, RB by SR equivalent to 1. So as the RB by SR is increasing, the trend of the graph is also increasing. 87 SR by 86 SR, and it will depend on time t. Now we can, so what I have been telling you since the last 10 minutes, so it can be represented by via a diagram. So we can find it to decipher the evolution of the metamorphic history of a rock, right? So I will show you what that diagram basically looks like. Let's draw a graph. This is my ti time, this is my tm, and this is the tm plus delta m, and this is today. Let us assume ये हम लोग का प्रेजेंट डे है. This is t of m plus delta m, and this is tm. Okay, tm represents for the metamorphic time, and tm plus delta m means for how long that metamorphism has been continued, right? Clear up till now?
Yes, sir. Yes, sir.
Okay, now, so this is my time in past. We are going back into the past, right? Now let's say, and yeah, I'm forgetting this 87 SR by 86 SR. This is my 87 by 86 SR strontium ratio in my y-axis, in my ordinate. Now, if there is a rock at this two-dimensional space, now as long as we are assuming that it haven't undergone any metamorphism, so with time your 87 SR by 86 SR will tend to increase like this. Okay, this is for the rock. This is the average of all the minerals because a rock contains several minerals. Now, for an example, if that rock has apatite, the trend line of apatite will be like this if it is biotite. Because apatite and biotite, in comparison to apatite and biotite, biotite has higher amount of rubidium because it can hold potassium in its system.
Potassium. Yes, sir.
Yes. and apatite is CF5PO4. It can hold
ठीक
calcium,
है
so the
स्ट्रोंशियम
so the concentration of rubidium will be less, and if the concentration of rubidium is less, the concentration of strontium will also be less, because your strontium is coming from the rubidium itself. And this is your Ka feldspar, potassium feldspar, potash feldspar. Now this is my metamorphic. Now these lines are going. These are continuing. These are fine up till now. And after hitting the metamorphic time period, what they will do, they will try to reorganize, they will try to redistribute it themselves, right? And after redistributing, they will come or converge towards
सर
the,
सर हेलो सर
yes,
सर अभी आपने वो जो बोला ना बायोटाइड अगर प्रेजेंट हुआ तो फिर उसमें रुबिडियम ज्यादा होगा क्योंकि वो पोटेशियम को होल्ड कर रहा है लेकिन सर अभी आपने बोला कि अपाटाइट अगर रहा तो फिर उसमें रुबिडियम लेस होगा सर ये तो सही है लेकिन सर अपाटाइट में कैल्शियम जो है वो स्ट्रोंशियम को भी तो स्ट्रोंशियम कैल्शियम को रिप्लेस करके उसका भी तो प्लेस ले सकता है
the major
प्लेस ले सकता है
the major structure in hepatitis is CA5PO4, ठीक है?
जी
CA
सर
CA is 5, okay, and it is bonded to P. So क्या होता है, उसका लैटिस स्ट्रक्चर और लैटिस शेप ऐसा है, डायरेक्टली जो कैल्स मतलब जो इन एपाटाइट यू कैनॉट रिप्लेस दोस कैल्शियम डायरेक्टली, ओके? The chemical structure or the crystal structure of the rock or the mineral has to be in such a way that you can break that crystal structure and you can replace that potassium easily, okay? The crystal structure of apatite is such that you cannot easily just go into the calcium, replace the calcium, because there are 5 calciums. The bonding is very intricate, समझ रहे हो?
यस सर
It depends on the way how the minerals are bonded with each other, the elements in the mineral are bonded. It also depends on the bonding factor also, okay?
जी
So
सर यस
that
यस
is why as compared to apatite, biotite में ज्यादा होगा, okay? So this is the line for biotite. But nice question, by the way. So this is appetite. Now, so come to the point. So what we are trying to decipher is, so we have reached the metamorphic time period. Now, at that particular time, metamorphism has occurred, right? Now, अगर इस time में metamorphism हुआ, then what I have said to you, that they will try to redistribute or reorganize, right? Now, if they try to redistribute themselves, so what will happen? They will converge to the rock. वो सब लौट के कहाँ पे आएंगे? रॉक पे आएंगे. And this is the point P, right? And from that point P, again there is no metamorphism. They will go fine. Apatite will go like this, biotite will go like this, K feldspar, biotite, apatite. Okay. Now from this point, it is the metamorphic age. And if we consider this entire line, this is my rock formation age. Now, the question is, if the rock has undergone metamorphism, how we will find the rock formation age? In order to do that, we have to do whole rock isochron. Means we have to take the entire rock, we have to cut it into pieces, we have to powder it, and we have to do a whole rock isochron. Then only we will get the actual age of the rock, and it is doable. Okay, and we have to keep one thing in mind: the metamorphism was not intense enough to form a rock scale change. It has to be limited to the mineral scale change. Okay, and if these criteria are fulfilled, then only we will be able to decipher both the metamorphic history and the rock formation age. Right? So this whole rock never changes its path, and hence we can take several pieces of the entire rock, which we can do and get the rock formation age. Is it clear?
Yes, sir.
Okay. Now, this was all about RBSR, isotopic systematics, or whatever else. Now, what we will do is we will go with the binary mixing, because what I think is in most of the colleges or universities, binary mixing, the concept of binary mixing was actually is not introduced properly, or uh, I don't know, but professors not usually uh, go through with the concepts of binary mixing. तुम लोगों का कॉलेज में हुआ है क्या बाइनरी मिक्सिंग?
नहीं सर, वो हाँ, सेकंड सेम में है। अभी हमारा फर्स्ट सेम चल रहा है ना।
Okay, so do you know that or do you did you ask your seniors that uh, binary mixing was covered in their syllabus? In your course curriculum, is it there?
ये सर थोड़ा बहुत है इंग्लिश में।
Oh, but still, I will teach you the concept of binary mixing, because if any student will see this video, so they will get to know about the binary mixing concept. So it's okay. I will go with the concept. So we will go with the concept of binary mixing. So what is basically binary mixing is? So so we often look for chemical and isotopic composition, right? For from different reservoirs, and when they mix, we always see a mixture, and we look for their chemistry, and their chemistry is also readily available. Now we want to go back, and we want to see how much is coming, how much mixture is coming, and from where it is coming, right? we, because we are always curious. Agar, for an example, if A and B is mixing and becoming or forming a product P, so we are always curious about how much A is there and how much B is there, right? We want to quantify,
यस सर।
or we want to measure the quantities of A and B, because we are very curious. If we are curious now, so let's take an example of an estuarine system, right? So estuary is a mixture of river and sea. So let's consider an estuarine system, and because it is a mixture of river and sea. So this is my estuarine system. So if there is a river and there is a sea, so from the river and sea, one thing is only coming, that is water. Let's say water is represented by x here, x of r and x of sw. So they are coming, contributing towards the estuary to form an estuary. So this x, this water, is particularly a fraction to form the estuary, right? So some amount fraction of water from the river, some fraction of water from the sea, contributing both to form the estuary. So the x in particular is the fraction to form estuary. So from this, don't worry, I will enter into the isotopic systematics. Don't worry. Now, so we want to quantify how much is coming from both the sources, right, to form the estuary. So we have to just go on a mass balance equation. So this much mass is coming from here, so this much is here. If we just put it like this or this or this, we'll just able to adjust. We'll try to adjust to balance the equation, right? Now, for an example, let's take the example of strontium or any particular system. So strontium. So strontium has several isotopes, right? 84, 86, 87, 88. And if we are telling strontium, then it means it is a mixture of all the isotopes. So SR of M, it equals to, let's say, let's consider, we are considering a mixture of from two fractions. That is strontium of A, fraction of A, plus strontium of B, having fraction of B. Now we know that if it is a two modal fraction, means fraction of A or fraction of B, if we combine them, we will get 1, right? Because the total should be 1.
Yes. Yes, sir.
So f of A plus f of B, if it is a fraction, then the summation should be 1, because we are considering fraction here. Now we can write if B equals to 1 minus f of A. Now we will substitute it in the equation. So SR M equals to SR of A FA plus SR of B 1 minus FA. Okay, so this is the fraction of water, as we are talking about estuary, this fraction of water and this fraction of water. Now what we will do is, in the basically to form the equation, because as we are considering water, water में क्या रहता है, तुम्हारा सी वाटर में थोड़ा सा सॉल्ट रहता है, राइट? And it is mixing with the riverine water. So we can do one thing, we can take a cation, or we can, to form the fraction part, we can divide SR with the help of Na. Let's say suppose, so SR M by Na, SR of Na of A Pa plus this Pa is the fraction of sodium, okay, coming from the source A or coming from the seawater, plus I will write Pa is the fraction of sodium coming from the source, because there are two sources A and B. So A में भी, A से भी कुछ सोडियम का सोर्स तो आएगा, मे बी इट्स वेरी मिनिमल, लेट्स से 0.0005 parts per mil. For seawater it will be higher. Strontium of Na of B, it will be Pb, or in place of Pb we can write 1 minus Pa. Okay. Now if we take, so this will be a equation, the fractionation equation. Okay. Now if we take two elements, let's say SRM equals to SR of A of F plus SR of B of 1 minus F. And another calcium, let's take C of M, Ca of M, Ca of A into F plus Ca of B into 1 minus F. I am showing this example or equation with rubidium strontium. You can do at your home with the help of samarium, neodymium. The process will be same. Okay, so the F will not change because we are talking about same two sources. So the F is not going to change, whether be it calcium or strontium, क्योंकि हमारा source same है. So we will calculate for F value. Plus Ca of B minus Ca of B into F. CAM minus CAB equals to F of CAA minus CAB. So F equals to CAM minus CAB, CAA minus CAB. हम लोग लिख सकते हैं, we can write this.
Yes, sir.
Okay. Now ये जो इक्वेशन था, दिस लेट्स टेक, ये हमारा मेन इक्वेशन था, सो वी विल कंसीडर दिस एज इक्वेशन 1. नाउ वी विल पुट द वैल्यू ऑफ f इन इक्वेशन 1. Putting the value of f in equation 1, we will get SRM. So the classes which I am taking for you guys, so is this class helpful for you guys? इस क्लास जो अभी तक जो क्लास हुआ है, उन क्लासों से तुम लोगों का कुछ फायदा हुआ है?
ये सर बहुत।
Okay. So CAB, CAA minus CAB. So see, for truly speaking, if you guys are, क्योंकि देखो मैंने जो syllabus, the syllabus which I have covered, so if you guys are planning on doing a PhD or anything, so these are the basic fundamental and strong points. So if you guys can catch these things up, or if you guys can just if you guys can just consider it for your studies, then I think these things will be helpful for you, क्योंकि मैं इसीलिए तुम लोगों को डेरिवेशन करके देता हूँ, क्योंकि दिस डेरिवेशन यू विल नॉट फाइंड इन द बुक, ओके? सो मतलब
यस सर। सर
मैंने,
हमारे
यस यस।
सर मेरे दोस्त ज्वाइन कर सकते हैं, लेकिन सर अभी हमारा सेमिस्टर चल रहा है। उसका एक क्लास पेपर है जो रिमोट सेंसिंग एंड आरजीएस।
हम्म।
तो फिर सर इसी वजह से सर ज्वाइन नहीं कर सकते।
ओके ओके।
सर
आई
नेक्स्ट वीक से ज्वाइन करेंगे।
I'm not telling about joining. What I am telling you, what I have been teaching to all of you guys. So these things, some of the things might be helpful for your competitive things. जो small questions रहता है. But in the broad term, if you see what I have been teaching to all of you guys, if these derivations and these the things which we discuss it in the class, so these are very fundamental questions in geoscience. Okay, so these fundamental parts are will actually, I think these fundamental concepts will going to help you in your further studies. What I think is so,
सर
because
ये जो आइसो सर आज आप जो पढ़ा रहे हैं जो आइसोटोप जियोलॉजी, सर इसके लिए कौन सा बुक अच्छा रहेगा थोड़ा बताओ।
for isotope geochemistry you can follow Gunter and Faure. Gunter
सर थोड़ा
Faure
फिर से बोले।
and yeah,
सर थोड़ा फिर से बोले।
Gunter Faure and Teresa M. Mensing. I am writing the name. Gunter Faure and Teresa M. I will send the PDF. ठीक है? Gunter Faure and Teresa M. Mensing. This is a very good book for isotope geochemistry. थोड़ा सा बहुत मोटा बुक है, बट पूरा पढ़ना नहीं है. You can just cover the parts which you need, and the book is very well written and the concepts are very clear. You can read this book, and I also have one another book. I will send it to you. Okay, I will send it in a drive link, so don't worry. So yes, so and SRB it will be, and for SRB it is 1 minus F, ठीक है? So 1 minus CAM minus CAB, CAA minus CAB. Now SRM equals to SRA CAM. So you guys are from the same college, all of you?
यस सर लगभग। सर हमारे यूनिवर्सिटी से
Hmm.
16, हाँ सर 15 से 16 बच्चे इनरोल किए हैं इस एग्जाम में।
तुम लोग कौन सा यूनिवर्सिटी से हो?
संबलपुर।
संबलपुर।
संबलपुर यूनिवर्सिटी है सर।
ओके
उड़ीसा।
ओके। संबलपुर एक्चुअली होल्ड्स द फील्ड वर्क फॉर जीएसआई. वहाँ पे जीएसआई का फर्स्ट ईयर
ये सर।
फील्ड वर्क होता है.
सर ये जो महानगरी गवर्नमेंट।
यस यस, it's a very good place for GSI field work. CAM minus CAB, so CAA minus CAB plus SRB. So if possible, if any of one of your friends or any students are planning to do PhD from abroad, so तुम लोग एक काम कर सकते हो, uh, mm, you can just put a great effort in your master thesis so that you can publish a paper. at your masters. So that will be very helpful. And it's not that hard to publish a paper. If your basic concepts are clear, you will be able to publish, so that you can enter into good institutions abroad. So yes, so this is the equation, right? Plus SRB, or we can do one thing. We can just take a common at CAA minus CAB. Okay, so SRA CAM minus SRA CAB minus SRB CAM plus SRB CAA. Okay, CAM and CAM, we can take these two common. CAM SRA minus SRB CAA minus CAB plus SRB CAA minus SRA CAB. Okay, now here also we can see it is following a, this is my M and this is my C. So y equals to M CAM plus C. This is our x. So it is also following a y equal to mx plus c type, right, Mono?
Yes, sir.
So it means if it is following a straight line equation, y equals to mx plus c type, means the strontium and calcium are not going to change. Okay, so if we can represent it in the linear form, like, let's draw a graph. Let's draw a graph. So this is a graph for strontium, this is calcium. So if we have two sources, A and B, A and B, so while going from A to B, if we mix A and B in different proportion, they will form a significant line, and it can be joined by a line, and it will be 0 0.2, 0 0.4, 0 0.6, 0 0.8. So source A has composition here and source B has composition here, right? So if we mix A and B in different proportions, they will form a straight line. So from this diagram, we will be able to tell that how much supply is coming from where. Okay, so depending on the fractionation of the elements, these two will form a linear trend. So कौन कितना fractionate किया, so ये हम लोग एक straight line से connect कर सकते हैं, right? Because this equation tells us mathematically it can be represented by a straight line. Now, so ये था हमारा with sources with same isotopic composition. Now, if we take a source with different isotopic composition, that will also create a mixture, and how the isotopic ratio of that mixture changes or varies, that we will discuss. Okay, so again, let's take strontium only, but with two different isotopes of strontium, 87 strontium and 86 strontium. Okay, so if we take A and if we take B, so these are my two sources, and 87 strontium of A and 87 strontium of B, we will get 86 में भी बाद में आ रहा है F1 minus F, right? हम लोगों को क्या मिलेगा, 87 strontium का एक मिक्सचर मिलेगा, right? now we will looking for an expression that will hold the composition of the mixture. So we can write 87 SR of M equals to 87 SR of A F plus 87 SR of B 1 minus F. Now, what is the meaning of SR in A? It means if we divide this SR with its atomic weight, we will get the moles. Means SR of A by atomic weight of SR of A will give me the moles, number of moles. And if
Yes, sir.
number of moles is multiplied with the abundancy, and sorry, number of moles is multiplied with Avogadro number, we will get the number of atoms. And if we
Yes,
get
sir.
the number of atoms, and if we will multiply with the abundancy of the strontium, we will get the number of strontium is present in the system, right?
Yes, sir. Yes, sir.
So हम लोग we will just reorganizing the equations, right, and nothing else. These are play of numerical and mathematics. These are all numeric deeds. This is a game actually. So strontium of A, atomic weight of SR of A into Avogadro number into abundance of 87 in A. So this is my term. We will substitute here. Okay. So it will look like 87 SR of M equals to SR of A, SR of A into Na into 87 abundancity of A into F plus SR of B, weight of SR of B into Avogadro number into abundancity of 87 in B into 1 minus F, right?
Yes, sir.
This is my 87 SRM equation, 87 strontium of mixture. This is my equation. So this similar equation we can write for 86 strontium. So just the number, mass number will change. 86 SR of M equals to SR of A of SR of A into Na into abundance of, there will be 86, okay, of A into F plus SRB, WSR of B, these will all remain same. Now I got a number into, only the abundance will change. 86 of B, 1 minus F. Now we will divide these two. 87 by 86 SR. We are interested for 87 SR by 86 SR. Simply we'll divide these two equation 1 and 2. 1 divided by 2, we get, okay. Now we will see by dividing these two equations what we obtain. Now it's simple. Now we can generally basically assume that the atomic weight of strontium and the strontium B is nearly equal. Okay, because in natural system the isotopic abundance does not change, क्योंकि natural system में तुम्हारा जो isotopic का abundancity है वो ज़्यादा change नहीं करता है, ठीक है. So मतलब source और spike में ज़्यादा change नहीं करता है. That is why we will just try to convey it like the atomic weight of strontium A and strontium B more or less equal. So we will consider it as equal for the sake of our calculation. Okay. So मतलब अगर ये तुम्हारा WSR A and WSR A for 86 and 87 अगर same हो गया, so it will cancel out. So no meaning of writing it, the atomic weight. So 87 SR or 86 SR equals to 87 SR of A. Okay, into Na into AB of 87A F plus 87 SR of B Na AB of 87 1 minus F divided by 86 SR of A into Na into AB of 86 F plus 86 SR of B into Na into AB 86 1 minus F, right? So Avogadro number will be same क्योंकि ये कांस्टेंट है.
Yes, sir.
Avogadro number will
Yes.
cancel out. Now 86 is stable. ठीक है. Abundance of 86. 86 is a stable isotope. अगर 86 stable isotope हुआ तो abundance of 86 in A and abundance of 86 in B will be equal. It will not vary.
Yes, sir.
क्योंकि ये जो भी
Yes, sir.
मिक्सचर से है कुछ फर्क नहीं पड़ता क्योंकि ये स्टेबल आइसोटोप है, वो तो कभी चेंज हुआ ही नहीं था. सो दिस टू विल बी इक्वल. दिस टू विल बी प्रीटी इक्वल, राइट. ओके. नाउ one thing we can write is that is 87 SR और 86 SR equals to, हम लोग अब क्या करेंगे, as the abundancy of 86 strontium is equal, we will divide the numerator part and the denominator part with the abundancy of 86 SR. Okay, so SR of A equals to into. Now there is one thing I would like to tell you. If we divide the abundancy of 87 SR and divided by abundancy of 86 SR, we will get the ratio of 87 SR by 86 SR. Okay, so remember this. 87 abundance by abundance of 86, we can write 87 SR by 86 SR. Okay, so SR A into 87 SR by 86 SR, क्योंकि हम लोग ने we are dividing the abundancy of 86 SR in the numerator and denominator part. Okay, F, it is A plus SR B 87 SR by 86 SR of B 1 minus F. This whole thing is divided by. So abundance of 86, this is, we have divided with the numerator and denominator. So these two, they will become 1, right?
Yes, sir.
So the equation will become SRA, only F will remain, plus SRB 1 minus F, सिर्फ ये रह जाएगा, SRA, SRB 1 minus
Yes.
and F,
Yes.
this will only remain. And we have started with SR M equals to SR A of F plus SR B of 1 minus F. So इसको हम लोग SR M लिख सकते हैं, right?
Yes.
So 87 SR by 86 SR of whole M equals to SR A, this SR A, this SR A by SR M divided by 87 SR by 86 SR of A of F plus SRB by SRM 87 SR by 86 SR B 1 minus F. ठीक है, so this is your final expression. Okay, and ये देखो, ये generally SRA by SRM, SRB by SRM, so it's in the, ये एक तुम्हारा फ्रैक्शन पार्ट में आता है. सो कैन यू टेल मी what kind of equation it is representing? It's in a hyperbolic form. Okay, x
Yes, sir. Yes, sir.
square by a square plus y square by b square, ये हम लोग करते हैं ना.
Yes, sir.
Yes, so this nature, so see, when we are mixing with different sources of isotopic composition, we are getting an hyperbolic form. Means hyperbola मतलब क्या होता है, वो हम लोगों का, या फिर तो कुछ बहुत ही छोटा, it represent terms in smallest order or it represent terms in the higher order. Okay, हम लोग मतलब either logarithm or exponential terms. So 87 SR, if we want to represent this or plot this in the graphical format, 87 SR by 86 SR in the y-axis, and this is strontium. So if this is my A, source A, and this is my source B, source A का part है. So if we connect these two from A to B, we'll get a hyperbolic path. Means the fraction of A and B will be mixing with each other, and if we want to connect them, if we want to just find out how much of A and how much of B is there, and if we just put the trend, or if we want to follow the trend, then we will get a hyperbolic nature of that curve. Okay, so trend, and it always depend on the fractions. So I think it is clear, right?
Yes, sir.
Okay. Similarly, you can do or that epsilon or e whatever of 143 nd और 144 nd. जैसे ही तुम RBSR systematics तुम derive किए हो, ये 143 by 144 is also in the similar fashion, and you can do, you can also obtain the binary mixing equation also. So yes, बोलो, any questions? Monu?
No, sir.
ओके, सो और एक काम करते हैं, जैसे कि कुछ दो तीन तुमको तुम लोगों को एक इस वीडियो में वी कैन डू वन थिंग इज आई कैन give you or show you 2 or 3 numerical problems also. Okay, so that numerical problems might help you in the competitive examinations. So okay, we will do 2 to 3 problems only, ज़्यादा नहीं करेंगे, उसी में कवर हो जाएगा. We'll cover up the space with that. So yes, let me write one problem. Let's start with an easy one. So let's take an example of a radioactive, let's say a radioactive substance has a half-life of 3 days, let's say, and it has a mass of 1.55 gram. Of this substance is left after decaying for 15 days. Determine the original value of mass. Can you able to do it? N equal to n0 e to the power minus lambda t. इसी से हो जाएगा. You can do and tell me the value. यू कैन डू वन थिंग, यू कैन, ये जो ई टू द पावर माइनस लैम्डा टी है, इसको तुम टी हाफ, मैंने क्योंकि हाफ लाइफ दे दिया था, तो तुम इसको हाफ लाइफ का जो फॉर्म है उसके साथ मतलब तुम डिराइव करके भी ला सकते हो, या फिर तुम उसको
यस सर।
इस
सर
हाँ इस इक्वेशन से तुम रिप्लेस कर सकते हो दैट।
सर एन जीरो, सर एन जीरो निकला 1.55 इंटू ई टू द पावर 30465।
एन जीरो निकला है, ग्राम में निकलेगा ना, तुम इसको
यस सर।
इससे रिप्लेस कर दो, इससे
सर इसको ऐसे भी तो कर सकते हैं, जो टी हाफ दिया है, टी हाफ को यूज करके लामड़ा निकाल देंगे।
हम्म
सर एन जीरो को सर ये जो 1.55 दिया है,
हम्म।
सर ये नंबर ऑफ न्यूक्लियाई या फिर वो जो
ये
एम
एन
दिया
है,
है आपने?
1.55 इज योर एन, एन मतलब
यस
एटलीस्ट।
सर।
हाँ
सर तब फिर सर ये तो आंसर होगा 1.55 इंटू ई टू द पावर 3.465 होगा।
ओके, मतलब मुझे आंसर नहीं पता क्या होगा, चेक करना पड़ेगा। तो लाइफ हैज हाफ लाइफ ऑफ
यस सर।
3 डे, सो तुमने क्या किया है, 3 डेज, ये इस
सर पहले
हाफ लाइफ ऑफ 3 डेज, सो हाफ लाइफ तुम्हारा 3 डे गिवन है, टी हाफ इक्वल टू 0.6931 बाई
6
लैम्डा। हाँ
सर ये निकला 0.231।
हम्म।
सर ये निकला 0.321।
ओके, सो लैम्डा कितना निकला तुम्हारा?
लामड़ा 0.321, सॉरी 0.231।
0.32 231।
231। यस सर।
ओके, सो अगर लैम्डा तुम्हारा 0.231 निकलता है, सो एन
तो
इक्वल
सर
टू एन जीरो ई टू द
ये
पावर माइनस लैम्डा कितना है,
माइनस।
0.231, टी तुम्हारा 15 है, बस
यस सर।
हो गया। एन इक्वल्स टू क्या, एन जीरो इक्वल टू
एन डिवाइडेड।
1.55 इक्वल टू डिवाइड बाई ई टू द पावर माइनस 0.231 into 15, that will
यस
be
सर।
your answer now.
यस सर।
Okay, so let me calculate now. तक बस देख लेते हैं।
सर ये ऊपर चला जाएगा ई टू द पावर माइनस जो पावर है, और वो निकल आएगा 1.55 इंटू ई टू द पावर
अब
3.465।
एक सेकंड, एक बार कैलकुलेट कर लेते हैं। फोर्टी नाइन पॉइंट सिक्स आ रहा है तो आंसर।
यस सर। यस सर।
यस।
सर ये निकला 1.55 मल्टीप्लाई में 31.97।
हम्म।
जी सर।
49.6, yes. So yes, let's do another problem. Hmm. A radioactive nuclide of mass 6 gram has a half life of 8 days. Calculate the during which 5.25 gram so nuclide would have decayed. ये भी कर सकते हो।
यस सर।
You can also do this, ये कर लेते हैं। Actually nowadays these type of question, basic fundamental questions are only coming in the competitives. So it's better to focus on the fundamentals. Once you are mm, making a stronghold in your fundamentals, then you can solve any kind of problem. Let me do also. Okay, so n equal to n0 to the power minus lambda k. Is for the
Look,
yes.
yes, sir.
Okay. Let's wrap this class for today. Okay.
Yes, sir. Thank you, sir.
Okay. Okay. Bye.
सर आप थोड़ा ये जो असाइनमेंट के कुछ प्रॉब्लम हुआ था सर इसको
Assignments.
सर आपको जो मेल किया है इसको थोड़ा
Okay. Okay. Okay.
इस ये जो असाइनमेंट 5 के रिगार्डिंग सर जो किया था सर उसको थोड़ा सॉल्व कर देंगे सर प्रॉब्लम जो हुआ
Okay.
यस
Okay. We'll see.
ठीक है सर
Okay. I will revert it back to you. Okay. Okay. Bye. হ্যাঁ মা বলো। হয়ে গেছে। এই তো এখনই শেষ হলো। হুম। হুম। যাবো। বলো। হুম। হুম। কি? হ্যাঁ হ্যাঁ। কি বলবো? হুম। কি করে বুঝবো? কোথা থেকে এলো? আচ্ছা। হুম। 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 ওকে। হুম। ওকে। মানে? ও আচ্ছা আচ্ছা, হ্যাঁ হ্যাঁ।